A rational function is defined this way as the quotient of nx and dx. Here, nx represents the numerator function and dx represents the denominator function. And both nx and dx are polynomial functions. And of course, the denominator function cannot be 0. If you recall, we have learned about the reciprocal function fx equals to 1 over x. And this is actually the simplest rational function. Its numerator function 1 is a constant function, which is a 0th degree polynomial function. And its denominator function x is a linear function, which is the 1st degree polynomial function. We have learned several important properties of the reciprocal function, including its domain range. It's an odd function, which means that its graph is symmetrical about the origin, etc. And now we're going to learn another very important property of rational function, which is the asymptote. If you look at the graph, you will notice here is a vertical line that the graph of this function is trying to approach but will never reach. This is known as a vertical asymptote. For this particular example, the equation of this vertical asymptote is x equals to 0, or the y-axis, which means that when x approaches 0, here, this negative sign here indicates x approaches 0 from the left. Then the function value approaches negative infinity. And when x approaches 0, this plus sign means that x is approaching 0 from the right. Then the function value approaches positive infinity. In general, x equals to a is a vertical asymptote for the function if the function value approaches either positive or negative infinity when x approaches a either from the left or from the right. And there is also a horizontal line that this graph is trying to approach but will never reach. And this is known as the horizontal asymptote for this function. For this particular example, the equation of this horizontal line is y equals to 0, or the x-axis. When x approaches negative infinity, the function value approaches 0. The negative sign means that the function value is approaching 0 from below. And when x approaches positive infinity, the function value approaches 0 from above. In general, y equals to b is the horizontal asymptote for the function if the function value approaches b either from below or from above when x approaches either positive infinity or negative infinity. Now, let's summarize some important properties for a rational function nx over dx. Since nx and dx are both polynomial functions, therefore, the rational function can be written in this form. As you can see, the numerator function is a polynomial function of nth degree, and the denominator function is also a polynomial function, but of mth degree. For now, let's assume nx and dx do not have any common factors. The zeros for this function is determined by setting the function to be 0 and solve for the x values. Now, since the denominator function cannot be 0, therefore only the numerator function can be 0, therefore the zeros for this rational function simply are the same zeros of the numerator function. The vertical asymptotes correspond to the zeros of dx. Don't forget, vertical asymptotes correspond to the x values that the function can never be. Therefore, they also correspond to the points excluded from the domain of this function. To find the horizontal asymptote of this rational function, we need to compare the degrees of the numerator function and the denominator function. If n is smaller than m, then the horizontal asymptote is the x-axis, y equals to 0. If n equals to m, then the horizontal asymptote is y equals to am over bm, in other words, the ratio between the two leading coefficients. And if n is bigger than m, there is no horizontal asymptote. Now let's look at several examples, and hopefully those will help you understand these properties of rational functions. Let's look at this rational function, which has a numerator function x minus 2, that is a linear function, and a denominator function, which is a quadratic function that can be further factorized into the product of two linear factors. First, let's find the zeros for this function. We know that the zeros for the rational function correspond to the zeros of its numerator function. Therefore, the numerator function x minus 2, set it to 0, we can solve for it, x equals to 2. This is the real zero for this rational function, and it corresponds to the x-intercept on the graph. Then the vertical asymptotes. Vertical asymptotes of a rational function correspond to the zeros of its denominator function. Therefore, we can find the zeros of this denominator function to be -3 and 1/2. And these also correspond to the equations of the vertical asymptotes. Now, because vertical asymptotes are lines that the graph of the function can never reach, therefore, these also correspond to the points that need to be excluded from the domain of this function. So the domain for this rational function include all real number except for x equals to -3 and x equals to 1/2. Next, to find the horizontal asymptote, we need to compare the degree of the numerator function and the denominator function. In this case, the numerator function is first degree, denominator function second degree, therefore n is smaller than m. Therefore, the horizontal asymptote is the x-axis, y equals to 0. And lastly, if you wish to, you can find the y-intercept of this function easily by substituting x equals to 0 and evaluate. And here's the graph for this rational function. As you can see, it has a vertical asymptote, x equals to -3, vertical asymptote, x equals to 1/2, and both -3 and 1/2 are excluded from the domain of this function. It has a horizontal asymptote, which is the x-axis, y equals to 0. It has a x-intercept, 2, 0, also a y-intercept, 0, 2/3. All of these agree to our analysis. Let's look at this example. For this rational function, the numerator function is a quadratic function that can be factorized as product of two linear factors. The denominator function is also a quadratic function. First, to find the zeros of this rational function is the same as finding the zeros for the numerator function. We set the numerator function to be 0, and we can solve for x to be -2 and 1/2. And both of these are real zeros, therefore they correspond to the x-intercepts on the graph, -2, 0 and 1/2, 0. Then the vertical asymptotes correspond to the zeros of the denominator function. We set that to be 0. We can find x equals to -3, x equals to 5/3. Both of them correspond to the equations for the vertical asymptotes. But also they correspond to the points that need to be excluded from the domain of this function. For the horizontal asymptote, we need to compare the degrees of the numerator function and denominator function. In this case, numerator function, quadratic with a degree of 2, denominator function again with a degree of 2. So in this case, n equals to m. Therefore, the horizontal asymptote of this function is the ratio between the two leading coefficients, in this case 2/3. And if we want to, the y-intercept can be easily determined by substituting x equals to 0 and evaluate, and we got the y-intercept for this function. And here is the graph for this rational function. Again, as you can see, vertical asymptote, x equals to -3, vertical asymptote, x equals to 5/3. Also, these correspond to the 2 points excluded from the domain of this function. Horizontal asymptote, y equals to 2/3, x-intercept -2, 0, x-intercept 1/2, 0, y-intercept 0, 2/15, and all of these agree to our analysis. Last example, for this rational function, the numerator function is quadratic, and it can be written again as product of two linear factors. The denominator function is linear. The zeros of this function are the zeros of the numerator function, which are x equals to -3 and x equals to 1, also corresponding to the x-intercepts on the graph. The vertical asymptotes are determined by the zero of this denominator function, which is x equals to 2. That is the equation for the vertical asymptote, but also corresponds to the point being excluded from the domain of this function. Therefore, for this rational function, its domain is all real number except for x equals to 2. To find the horizontal asymptote, again, we compare the degrees of the numerator function and the denominator function. In this case, n is bigger than m, therefore, there is no horizontal asymptote. And also, we can find the y-intercept by substituting x equals to 0 and evaluate the function value to be 3/2. So here is the graph for this rational function. Again, we have a vertical asymptote x equals to 2. There's no horizontal asymptote. We have two x-intercepts and one y-intercept. But for this rational function, if we use the synthetic division or long division, we can rewrite it as x plus 4 plus 5, the remainder from synthetic division or long division, over x minus 2. And this x plus 4 here corresponds to a slant asymptote, which has the equation y equals to x plus 4 on the graph corresponds to this 45-degree line. So slant asymptote is something that only rational functions with n equals to m plus 1 have. In other words, this rational function has a numerator degree that is 1 degree higher than the denominator degree. Then this rational function will have a slant asymptote determined this way.